The broadcast is now starting. All attendees are in listen-only mode.
Hey, good afternoon, everybody, and this is Dr. Mansour, and this is the session of the FE7. The one had been postponed twice or moved twice, in fact. Sorry for that. Too many activities for me or commitment from my end. So thank you very much for coming today. I know it's a working day, and we are going to meet this weekend, by the way, and I found that the weekend already I have the Saturday and Sunday. So this coming Saturday, so today is the 5/6, and this is the FE7. So today is a 5/6. We are going to spend as many hours as we can today. Even the attendees today, they are not too many, but I will do my best here. This coming Saturday, from 4:30 to 8, we have a session, and I noticed that Sunday I have the whole day, which is from 8:30 in the morning to around 4:30 in the afternoon with the 1 hour lunch. So I will try to wrap up the chapters that I need to cover in these days, and we will do our best to cover as much as I can. So I'm still following the NCEES, the FE reference book 10.0, and the problems that they published last July, the 100 problem, the FE civil practice. So last time we were talking about the stress and more circle and all these things. I hope that you get a chance to look to these things here, and the equations are given here. And this is the angle to theta, the one I was telling you, the orientation. They did not give you the equation, but they are assuming that we know how to get the angle to theta. And more circle will give you double the angle. I need you to remember double the angle. Double the angle. The Professor Moore, when he took the equations and converted to a graphical solution, it ended to be double the angle. So I need to be aware of that. So all these equations we talked about it. This is the radius, which is r. This r here. This is the radius from the center to the point on the circumference. And I don't expect that you are going to draw more circle, but they might give you a more circle on the exam and ask you what is this and what is this. So after we locate the 2 points, because when you locate 2 points, and these 2 points, they must be given like the practice problem that we were working. Either the problem number 33 of the FE civil practice of the NCEES practice problems. After you plot the given information, or in relation to the sample problem 6-15, the one we talked about it last time, 6-15, which is basically, instead of giving you the diagram, he's giving you in form of sigma x and sigma y and tau xy, which is a shear stress and the 2 normal stresses. So we need to be familiar with that. Moving to the other stuff, let us go right now. Torsion, we talked about torsion. Torsion is important, and I need you to be aware that torsion, the tau, there are 2 equations, torsion. Torsion for circular shafts, and the circular shafts could be either solid or hollow. So if you have a solid shaft, so they gave us the radius, and we need to calculate the polar moment of inertia. Also, if it is a hollow shaft, so the inside radius and outside radius must be known, or the 2 radii must be known. So this is for circular shafts. Torsion also for non-circular, okay, non-circular shafts. The equations that they gave us will look to the NCEES, and again, we need to make sure that we really understand. The two equations related to circular shafts, one is a tau is equal TR divided by J. This is the first equation, which is given as here, tau is equal TR divided by J. And I needed to know that this is for the thick-walled, the wall, okay, either solid or thick-walled. So thick-walled. And they define the thick-walled as the when the thickness T is greater than 1/10 of the radius. And J is the polar moment of inertia, and the polar moment of inertia in the static section, we know the polar moment of inertia is basically, it is Ix plus Iy, by the way. This is the equation that's given. Torsional strain, this is another section given, where the angle phi, which is the angle of twist. This is the second equation I needed to be aware of. The angle of twist, which is, they call it phi, is equal TL divided by GJ. So those are the two equations that I needed to be aware of. And the angle phi is the total angle in radians of twist, angle of, normally expressed in radians. T is the torque, and L is the shaft. So basically, if you do have a shaft, and this shaft is subjected to torque, T, either solid or hollow, but the hollow shaft, we need to make sure it is defined as a thick-walled. So the angle of twist, which is the angle phi, normally when we do this in the lab, and I'm sure that we draw a line on the surface of the shaft, and after we apply the torque, T, this point A, if this is A and this is B, point A is going to be here at one point of time. So this is A prime. Okay, and this, the angle here, they call it phi, the angle of twist. These two equations, we need to know how to use them. The equation here, let me just they didn't tell you in the NCAAS that this is a tau max, because if you look to a circular shaft, sometimes I use my tools here, the one that has some circles, in order to avoid this funny shape. Let me do it. At least I can draw a, still will be a little bit because of the camera, but at least it is like an, okay, so if the if the center is here, and I drew this last time, and I said that the shear stress due to torsion is going to vary linearly, and the maximum is going to be on the outer fibers of this shaft. So this is the maximum shear stress. So this is a tau max, which is on the outer fibers, and this is the center here. So there are some books or mechanics of materials books, obviously the one we teach this subject, that they say tau at any radius rho is equal T times rho divided by J, where rho is a variable radius, rho, starting from 0 all the way to R, which is the radius. And the tau max will occur on the outer fibers when T is equal, tau is equal TR divided by J. So I need you to know that. This is, by the way, this is within the elastic stage, where the material is still elastic. But if you keep twisting or applying the test, or continue the test, or applying the torque, you will find that, let me draw another two of these just to show you the variation of the stress as we exceed the elastic limit. Because the question they ask, we answered it last time, if I remember, and I said that probably the wording a little bit, it could be much better. So, so if this is the same shaft, I hope that I use the same radius here. So if this is within the elastic stage, if you keep twisting the shaft and it goes beyond the elastic, what is happening? The outer fibers, already it has the tau max. So the outer fibers cannot take any additional stress. So the stress, okay, the shear stress is going to transfer to the inner fibers, okay, and it will start to carry, okay. So the stress start to increase, okay. Let me add another one here, okay, and something like that, okay. So the stress will, here is a tau max, and the next fibers to the outer fibers start to carry the maximum until this is called elastic plastic stage. And finally, when the shaft reach the entire plastic stage, or when you'll find all the fibers will be carrying the same amount of stress, which is like that. All the fibers. Okay, this is the fully plastic, and after that the failure fully plastic. And you will find these distributions are given in mechanics of materials books. They are not given in the, so where all the fibers, this is the tau max, where all the fibers reach the maximum shear stress, and after that the shaft will fail, or the specimen will fail. And this is what we I'm sure that you did this in the lab. And let me see if I still have. I'm carrying a box with me from Las Cruces, New Mexico, where I have all these fancy tests that we used to do, which also did it here at Fresno State. Yeah. This is a torsion test that we did. And also this is a torsion test that we did for a tube. Let me show you. So if you look to the torsion test that is done for steel, here it is. This is a steel shaft. It was held, here it is. This is a portion that was held at the grips of the machine. And this is how it looks like after failure. So we keep twisting, as you can see, even the lines. Okay, so it is almost perpendicular surface, because the steel is a ductile material. So ductile materials, when you have a shaft ductile material subjected to torsion, okay, I needed to know that also. This is okay. You will find that the failure plane is almost perpendicular. Okay, the failure surface is perpendicular. Okay, so this is the ductile material, like steel or aluminum or brass Okay, all these. So the failure plane is almost perpendicular. And in order to show the students that there is a difference between brittle and ductile, so I used to carry a chuck. Okay, chuck, as you know, we're no longer using chucks nowadays, but it was fun to write on the board with the chuck. You will find that if I have a box here. I used to have a box here. Okay, but unfortunately not. Is gone. So try to get a one full base. No. So if you let me try to do it. So if this chuck as a brittle material like concrete, if you try to twist it, and hopefully I'm a strong man today, here it is. You'll find that the failure plane is almost 45 degrees. You see, it is not normal. You see here it is the surface. These are the two pieces here together. So the failure plane is 45 degrees. Why? Because the stress causing failure. So if you look to the piece of a chuck, you'll find that the failure is like this. We need to know that because sometimes they give you this kind of illustration and tell you what type of failure is that. This for brittle materials, brittle materials, okay, like chalk, okay, or concrete, famous construction material. So the failure mode is different. Steel versus which is a ductile material versus the brittle material like piece of a chalk or something like that, or cast iron or concrete. Okay. This is a tube where we put some solid piece here, and this is where the machine is gripping this, and we twist it. As you can see, it is this is after the torsion has been applied and we reach the failure. So I need you to be aware of these things. That is the stress causing failure here. By the way, this is if you look to the shear stress. Here on this element, you'll find that the shear stress, okay, either this direction or this direction, both of them are equal. Okay, so the failure mode here, which is perpendicular to the axis or of this shaft, is because of the shear stress. Here you'll find that this is due to normal stress, which is this way, normal stress, okay? And the normal stress from the shear stress is almost 45 degrees, because if you go to Moore circle again, Professor Moore, he did that. So this is sigma, and this is tau, as you see in the NCEES book. You'll find that the angle between the tau max and sigma max is 90 degrees in Moore circle. Okay, but the Moore circle is always twice. Here it is. If you go to the book, and I'm reading from the NCEES book on page 133. If you always, as I said, that try to get this book. So this is the so tau max is here, which is basically the radius. And sigma max is here, which is one of them is called the maximum principal stress, which is sigma A and sigma B. Here they define it here. Here it is sigma A and sigma B. Sigma A is the max. Okay, sigma A, which is this one here, is a maximum principal stress. And sigma B, as in boy, is the minimum principal stress. Okay, the word the principal is very important. Here it is. They mention here it is. Principal. The principal stresses where the shear stresses are zero. Okay, so this is on page 133 of the NCEES. So this angle here is 90 degrees. So the diagram I put here for the brittle material, which is, or brittle materials, you'll find that the sigma normal is 45, like this. Here it is. If you come here, and this is the angle theta here, this angle theta is equal 90 divided by 2, because we see that more circle always give that, so 45 degrees. And this is the explanation why this failure is 45 degrees. Here we will feel under the maximum shear stress, and the shear stress is perpendicular to the axis of the shaft. So I need you to know the distribution is very important, and you need to know the failure mode. And I have many problems in my books, the one I'm preparing. Hopefully that one day it will be done. So we need to understand these things, because it could be a target for a question on the exam. So torsion, I needed to be aware of that. For hollow thin walled shaft, they are coming with this equation. Tau is equal T divided by 2 A sub M times T. T is the thickness of the wall shaft, and the area of the solid shaft of radius equal to the mean radius of a hollow shaft. So the A sub M is equivalent area, okay, area of a solid shaft of radius equal to the mean radius of the hollow shaft. So these are the NCAAs. And I have some problems here when we went over this. Hopefully that you can look at it. And the following subject is very, very important, and you are going to see it in the PE later on in the PE, and either the national exam or the seismic, we need to understand. So this section is given by this title beams, and this is what's given in the NCAAs. So shearing forces and bending moment sign conventions. They agreed on the following sign conventions, and these are standards. For bending moment, this is positive bending moment, where compression here and tension here, which normally we refer to as the happy face. So if somebody is happy and get the results from the NCAAs, you receive a letter, congratulations, you passed the FE. So this is a happy face, so compression tension. Okay, so this is a positive bending moment. The other one is the opposite, the unhappy face. So this is tension and this is compression. So this side is tension and this compression, and this is the negative bending moment. So this is as far as the bending moment M, which you are using letter M. The shear, they agreed that this go up and this go down, which is a clockwise, and this go down and this go up, which is a counterclockwise. So this is a clockwise and this is a counterclockwise, the positive and the negative shear, and this is V, the shear. And by the way, and we'll go over shear moment diagram shortly, and you will find that for shear, I will tell you a very simple rule. Just start from left, and anything goes up, go up, anything goes down, go down. You are going to follow the sign convention blindly without really thinking too much about it. But as far as moment, we need to know where is the positive and where is the negative, because in design, either for steel beams or concrete or any kind of any beam in general, it doesn't matter. You need to know where is the positive, or where are the positive quantities and where are the negative quantities. Otherwise, we will not be able. So if you do have a cantilever beam like this, and let's assume that this cantilever beam, okay, it does have a load, whatever the load is, a distributed load, and this is A and this is B and this is W. Let's assume this is 2 kibs per linear foot, and this is L is equal 8 feet, for example. And let's assume that the cross section, which you are going to use it later on to determine the maximum bending stress or flexure stress, let's assume this is 4 inches by 6 inches. Okay, so we are expecting this beam will deflect as shown. It will go down, which we are going to see the equation for deflections, by the way, they are providing us. So this is the maximum deflection, which is delta B. Okay, and they call it YB, by the way, I believe in the book here, or sometimes they call it VB also. We'll see deflection. These are the deflection, which is the maximum deflection. But this is a negative bending moment. Why negative? Because the beam is doing this. So this is tension and this is compression. So this is the unhappy phase. Okay, so and this is why when you draw the shear diagram and the moment or the shear and moment diagrams, you will find that we will have the following. So so you'll find that the shear, basically I have reaction here A sub y, and we have A sub x, and we have the fix in moment, which is M sub A. So this reaction here, the A sub x obviously is equal 0 by inspection, and this is 2 times 8 is 16 kips. So A sub y is 16 kips. The moment is equal 2 times 8, 16. It will be acting at the centroid. The centroid is 4 feet. 16 times 4 is equal 64 kip feet. So the shear, which is V, we are using letter V for the shear diagram or the shear forces. So you are going to start from left. I will find that I have 16 kips. I will go up 16 kips, and after that I will lose 2 kips per linear foot as indicated. So this is a positive shear. So I start, this is 16 kips here, and every 1 foot I'm losing 2 kips because 2 kips acting down. So this is the shear. The bending moment diagram, since it is negative, normally we draw a reference line, we call it datum. So the bending moment here is equal 0 at the free end, and the bending moment is 1 degree higher than the shear. So in this case, you'll find this is a second degree parabola or parabolic like that, and it is a negative bending moment as we indicated because it's unhappy phase. And this magnitude here is 64. 64, by the way, this is the area. If you look to the area of this triangle is equal 1/2. What is the base? The base is 8 feet, and the height is 16. So you'll find that the area under the shear diagram, this is 4. 4 times 60 times 16 is 64 kip feet. And we're going to see this relationship shortly, that the area under the shear diagram is representing the change in the bending moment between 2 points. Okay, we're going to see that because there are 2 equations. I believe we're going to see them. Okay, the famous 2 equations, that the dV by dx, the slope of the shear, will give you negative W, and the dm by dx equals V. These 2 relationships are very, very important. And they are given here, by the way. Let me see how they did it. A little bit different from mine, probably. Okay. So the relationship between the load and the shear and the moment equations are, and this is in my chapter on page 34, which is basically taken from the NCWS, all this, the section. So it is Wx is equal dV, okay, with respect to x dx. Okay, so dV by dx is equal W. Okay, I put negative W here. He expressed it differently. He said that it is Wx is equal negative. So negative here is not a typo. It is part of the equation. And dm by dx is equal V. These 2 equations are very important, which is, we can say slope of shear equals load with the negative sign. Okay, this is the first equation. The second equation is the slope of the moment diagram. If moment diagram is equal shear at any point, shear. And this is very obvious from this sample problem here. If you look to the slope, this a negative slope. Is this correct? Do you remember from calculus 101? Let me remind you. This is x and this is y. What is the slope? Slope, we know it, a slope is a rise over run. Let me just move my camera here. Or it is simply slope is the dy by dx, another dy by dx. Or another way is tangent theta, where theta is the angle. So those are the 3 definitions that we We know it from the the math or the calculus. So the slope, all the slopes here are positive slopes. Positive, positive. The slope here is negative. This is why if you have your calculator, and I hope that all of you already set whatever calculators you are going to use. So the angle here, or we use a tangent. If you use a tangent theta, where theta is the angle with the x, if you'll find that this line here, x has a zero slope, by the way, zero. So if you enter the angle 0 and say tan, it will give you 0. Here it is, 0. And any angle between 0 until 90, all of them are positive. So the 60 degrees tan, positive. All these are positive until you come to the y. The y, this angle is 90. If you enter 90 and say 10, it will give you an error. It will give you invalid data, okay? If you look to your calculator, you'll find that the tangent of 90 degrees is going to give you an error. Because basically the y-axis has no slope. This line has no slope. No slope. This is what is meant. Okay, no slope. This line x is zero slope. These lines are positive, these are negative. So if you look to the shear diagram, you'll find this is a negative slope. So we are saying that dv by dx is equal negative w, or negative dv by dx is equal w. What is the slope? It's the rise over run. It is 16 divided by 8 will give you 2, which will give you the load. Okay? And the same story, dm by dx. dm by dx is equal v. If you look to the slope, this is the second degree, by the way. The slope of the bending moment here is equal what? dm by dx. What is the slope of a curve? You draw a tangent. A tangent is horizontal, and the horizontal has a zero slope. This is why the shear is equal 0. And after that, the slope is, as you can see, and all these slopes are positive because the shear is positive. So the point I would like to make here is very important to know the positive and negative shear and the positive and negative bending moment, because later on we are going to look to the design for concrete. For example, if this is, let's assume this section, which is a very small section, but let's assume that this section is made of concrete. So the tension at the top and compression at the bottom, where should I put the rebars? We put the rebars along the tension side. So these are the rebars, the steel rebars. Okay, it should be along the tension side because concrete is very strong in compression, which is the bottom side or bottom, okay, below the neutral axis, and it is very weak in tension. So this is why we put the rebars. This situation will be different if I have an overhang beam. Okay, a beam that like this. With this we call it overhang. Overhang from one end, overhang beam. Okay, this beam, let's assume that is carrying a distributed load also, or even a concentrated load. Let's make it concentrated this time. P is equal 8 kips. And this A, I will call this is A, and this is B, and this is C. And let's assume dimensions are given, and I will give you this like a quiz, because we need to solve many problems, by the way, to make sure that we really understand, because during the exam we don't have enough time, so we need to master the subject. Okay, let's assume that this is 10 feet and this is 5 feet. What I will give you, I'll give you only 2 minutes. I need to find the reactions at A. We have A sub X and A sub Y. And we need the reaction at B. I need to give you 2 minutes only to do this for me, okay? So let us see the test. You have your calculator. Always bring your calculator or calculator that you are going to use on the exam, and try to master them, because I need you to understand or try to practice. I know you are using, and use it in your daily basis, by the way, daily work. Let me wait for a couple minutes. Right now, 5:08 California time. We will wait another 2 minutes and okay. As all of you know, the exam that sorry, I give you only 2 minutes. As you know, the exam is 5.5 hours. 5.5 hours is what? About 330 minutes, I believe. 5.5 enter 60 times. Yeah, 330 minutes. And the number of questions, they will give you 110, by the way. Okay. So if you look to this 110 questions and you have only 330, that means that we have what? 3 minutes? So 110 divided, yes, 3. So 3 minutes per question. So we need to master the subject such that, and this is including the search, by the way. There are some equations here, some tables, some charts. You are going to master searching, okay, this book, PDF. You enter the keyword and you should practice. You can download this for free from the NCAAS the moment that you open an account with them. So the NCAAS, and all of you, I'm sure that you are familiar with that. You can download the book and as a PDF, and you start to search, because I need you to know exactly where are the information and the and so on. So I wonder, I did it very quick. If you agree with me, that's good. If you disagree with me, don't take me to court. Let us, okay, let us resolve. Okay, A sub x obviously by inspection is equal 0. This load is acting down. So in order to find either reaction A sub y or B sub y, I can sum moment about A to get B sub y. So 8 times 15. So if I sigma moment about A equals 0 and the clockwise is moment, positive is up to you, by the way. You can say counterclockwise is positive. So it is 8 times 15. Okay. I don't know if this reaction going up or down. You can assume it. Okay. But I know this is clockwise moment, so this must go up. It has to go up, which is B sub y. So it is negative B sub y times 10 equals 0. If you solve for b sub y, 8 times 15 is 100 and what? 120 divided by 10 is equal 12 kips. And it came out to positive. That means that is up. So this is b sub y is 12 kips up. Okay. This is down and this is up. This must be down because I need to satisfy sigma force y must be 0. So if 8 coming down and 12 going up, this must be 4 kips coming down. In fact, in seismic design, I see some of you, I saw some names from the CE 137 class, the seismic. Yeah, this morning, it seemed that I need a secretary to take care of my my schedule because I have too many activities, and sometimes I forget this. Even sometimes I forget my medical exams and my lab work. So I'm writing everything, but the problem is who can remind me with the event. So I discover, oh, I have a conflict here. Oh my God! So I have to So and there is a joke about that when I used to go to the grocery to buy some stuff for the house. So my wife gave me a list. So before the list, she told me that bring this. So I go to the store and I get most of the stuff, but I forget some stuff. Where is this? Where I forgot. Okay, next time I'm going to give you a list. Okay, so she writes a list for me and she gave it to me, and I go to the store, and again and come short. What happened? I gave you a list. I tell, oh my God, my wife, sorry. I need somebody to be with me to remind me that I have a list. Okay, so, okay. So anyhow, so since then she said that, don't worry, I will take care of the grocery. I will buy the grocery because you cannot be really reliable in this. So anyhow, I saw some of you are taking this force, by the way, in seismic design, we call it uplift force. It's called uplift force, okay, which is because if you push this down, in fact, the deflected shape of this beam, if you draw the what we call it elastic curve, we're going to see the elastic curve later on, okay. The elastic curve is going to be like this. And in mechanics of this is called elastic curve. Elastic curve, okay, which is a deflected shape of the beam. Okay, and we need to know this. And as you can see here, tension top, compression bottom. And this is going to give you the shape of the bending moment. We're going to draw the bending moment shortly, because here it is. Tension top, compression bottom. What does it mean? It means that the bending moment is negative. And you are going to see it shortly, that this is the case, or this is true. Okay? So, reactions are important, and we need to double check how to get this. I know I'll cover this in statics, but if you continue the discussion here, and we are going to draw the shear and moment diagrams for this overhang beam. And here it is. Oops, sorry. So this overhang beam, and let me give you another 2 minutes to draw the shear moment diagram, which is a V and the M. And when you receive my notes, I will try to scan it and send it to you immediately. I know I know some of you ask me about the recorded sessions. My webmaster is working on something right now, recorded sessions. I have all the sessions are recorded, the sessions that we had so far, recorded sessions, which we call it on demand. You will have access to it. He's working on something. He'll try to put them on our website somehow, and instead of giving you the link to Google Drive and all these things, because I'm really busy. So he will take care of that, because I told the webmaster I'm really busy. I need to take care of these things for me. So he's working on it. He's coming tomorrow at 4 o'clock Friday, and hopefully that we will send you instructions how to get access to these recorded sessions. Okay, so so this is what we're going to do it. And when you receive the notes, I will scan it and send it tonight before I leave. Okay, so this is V and this is M. Okay, and the V normally keeps. Moment is kept feet, is force times distance. As we know from statics, moment is equal F. Moment is equal force times distance. We talked about that. Okay, so it is a force times this. So if you draw the shear diagram, as I told you that it started from left. Okay, it started from left, and anything goes up, go up. Anything go down. So the 4 kips is down. So I will go down. 4 kips is down, and I will move straight. I will tell you why I move straight. Draw nice here, and this is 12 kips going up. The reaction, we said that 12 kips. I hope that all of you got the same numbers. If you, as I said that, so 12. So this will put me 8 above the baseline, and after that I will go straight until I hit the 8, and the 8 will bring me down. You have to close it. Okay, there is no. This is positive, and this is negative. So this is 8 kips here, and this is 4 kips here. So my drawing is not to scale, but it's good enough for government job. Okay, so or state job if you work for the state. No, but try to do your best while you are studying. I'm not asking you to use a straight edge, but so this is the shear diagram. Okay, when I went 4 kips, why did I go straight from here to here? This is A, from A to B. I went straight because we do have an equation. It says dV by dx is, let me put it negative sign here to match the, is equal W, which is this equation here, the one I showed you. Here it is. This is the original document. Here it is. So this is the NCEES book, page 135. Page 135. So W sub x, okay, or Wx, okay, is equal dV by dx, and there is a negative here. You see this negative sign here? This is not a typo, as I told you. This is part of the equation. So what is the load between A and B? Nothing. So I need a slope to be 0. What is this line? This line has a slope 0. Do you remember the x-axis? Has a slope 0. Okay, and the same story with the other one. If you look to the bending moment, I need you to know key points. The bending moment at C is equal 0. And the bending moment at A is equal 0. Why? There is a very important rule, and I'm sure this for those who are attending the Fresno State in CE1 theory, okay, or even for 121. There is one very important rule normally I mention in the class, and I ask the students to remember this rule very well because it will help them. The bending moment, here is the rule. The bending moment at any point along the beam can be calculated either from right or from left. So if I am at C, I can calculate the bending moment here or determine the bending moment at C either from right or from left. Which one is easier? Right. What's to the right of C? 0. 0 will produce 0. But if you look to the left, you will find also 0. The same story at A. The bending moment at A, it could be calculated either from the right section or the left section. Left section is easier because what is to the left of A? Nothing. Nothing will be. So I know 2 key points, 0 and 0. Okay. Remember, if there is a concentrated moment here, and I will talk about this later on, yes, the moment at C is not 0. If there is a concentrated moment, but we don't have a concentrated moment, as you can see. So in this case, if you look to this area, this is 4, and this is 10, so this area is 40. And this is 8, and this is 5, this is also 40. And amazingly, you'll find that the 40 negative and the 40 positive must add up to 0, because I know the bending moment here is 0. So adding all the areas of the shear diagram must give you the bending moment, okay, which is given, by the way, in the NCEES like this. Here it is. The change in the shear between 2 points is equal to the area under the load diagram, and the change in the bending moment on page 135 of the NCEES. Or you look to my book, okay, it's over there also in the chapter. Here it is. It is given here also, okay, if you don't have the NCEES. This is on page 34 of this chapter, 34, okay. So these are the change in the shear between 2 points, V2 minus V1, is equal to the integration of the load, okay, with the negative sign, because the negative sign is here, between 1 and 2. And the same story, the change in the bending moment is the area under the shear diagram between the same 2 points. So these equations are very, very important, and it will help you. So if you look to the bending moment diagram right now, the one we need to okay, I will answer you. One of you is raising, have a question for me or a correction if I did a mistake here. Catch my mistakes, by the way, sometimes because I'm tired or because I'm thinking about something else or because of age, something like that. We do mistakes. Nobody above mistakes, including the President of the United States. But we need to minimize our mistakes here, and also in the exam, we need to minimize our mistakes because we need to pass. So if you look to the bending moment, so I know 2 key points. I know the bending moment is negative from the beginning to the end because the elastic curve. If you don't know the shape of the elastic curve, you're still able to find, because I can look to this point B as a point, and what will be the bending moment here? Again, the bending moment here, either from right or from left. Right is much easier. 8 times 5 is 40, and it's just going to bring the beam down. Bring the beam down like the cantilever. Here it is, bring the beam down, but this is distributed load, this is a constant. So it is a negative, and it is linear. Shear is 1 degree higher than the load, and the bending moment is 1 degree higher than. So it will be like this, and it is negative bending moment. And this value here is 40. Because if you look the bending moment at B, instead of right, I will use my left side. This is 4. 4 times 10 is still 40. So from either end, because the moment at any point along the beam can be calculated either from right or from left, and you should get the same answer. If you didn't get the same answer, that means that there is something went wrong in our. So the positive and negative bending moments are very important in shear, and I have a lot of problems here. Going back to the to page 34 of this chapter, chapter 6. But before I proceed, I need to grab a question from one of you or a correction. The question is the maximum shear in the beam is 8 kips. I have seen some use 12 kips when doing the stress check. Okay, what about that? Let's wait until our friend is asking. When we calculate I'm coming. You are ahead a little, but it's a good question. We can consider this question. Okay, here we have 8 kips here. Okay, and here from here to here is 12. Okay, which is basically the reaction. Okay, the question is, our friend is asking, what is going to be the maximum shear, the Vmax, in this scenario? Shall we consider it to be 8 or shall we consider it to be 12? And why we need the Vmax? Okay, because we are going to calculate 2 types of stresses. They are coming. 2 types of stresses. okay, which is tau max is equal VQ over IB, which is the shear stress due to bending. Okay, and the other one, which is sigma, which is a bending stress or flexural stress. There are two equations. It is M Y over I, and sigma max is equal MC over I. Okay, so those are the equations. Hopefully I'm using the same notations. Let me just make sure, because sometimes the NCAAS, they are using, okay, some kind of here it is, here they are. If you flip the page, okay, if you go to page 38 of the chapter, it's called stresses in beams. So sigma x is equal to negative my over I. Okay, let me stick with the notation they are using, my over I, and they put negative here. The normal stress in a beam due to bending, negative my over I. I will tell you why they put negative. Okay, and the bending moment, and I is the moment of inertia of the cross section, and the y, the distance from the neutral axis, okay, to the fiber, which is shown here. The bending stress, or sigma, this is a sigma or flexural stress. It's called bending stress or flexural stress. If you flip the page, section figure 616, okay, so this is a neutral axis or neutral surface. And if this is a cross section of the beam, which is B and H, let's assume that. So if this is a cross section, okay, so you'll find that the sigma max is here. This is sigma max. And in this case is a simply supported beam. So how the beam will deflect, as you can see, it will be like this. This is compression and this is tension. So the top fibers will be under compression. So this is sigma max compression. And this is here a sigma max tension. And the neutral axis equals 0, because the equation sigma equals to my. Y is measured from the neutral axis, by the way. Y, the distance y, is measured from the neutral axis. So the y is measured this way or this way. And the y is equal 0 here. And the y is going to increase until we get the maximum. And the maximum sigma is equal MC over I. And the reason this is a general equation, why they put positive or negative, because as you can see, compression and tension. So this is compression C, and this is tension T. And the compression is negative, and the tension is positive. My grandfather and your grandfather agreed on that. Please let us stick with this, because this is for the bending stress. The shear stress, which is a tau, here it is. On page 38 of the chapter, tau xy is equal VQ over IB. Very important equation. Okay. This is called a transverse shear stress. So there are two types of stresses. You'll find that the bending stress, all this is related to bending stress. Here it is. Okay, all this, okay, it does have three names. It's called bending stress. And we need to know all the names just in case on the exam, because the exam is written by engineers like you. In the future, after you finish your FE and you get your PE, you will write questions. The NCAAS, they seek engineers to write questions in addition to the professors and whatever. So sometimes everybody is writing the question and using the language. We need to be familiar because there is a variation from one person to another. Bending stress, or the other one is called deflection stress. The other name here is the normal stress due to bending. Normal stress due to bending. It's a long name, but we need to be familiar with it. Okay? The maximum normal stresses in the beam due to bending is given by this equation. MC over I right now is not MY, because right now the beam is like this. Here it is. This is the cross section of the beam. Assume it's a rectangular one, not a T-beam. Okay? So if this is B and this is H, so the centroid is somewhere here. So the axis that go through the centroid, we call it neutral axis. Let me call this as NA. And I will call this as H from here to here. This is the neutral axis, and this is the centroid C. Okay? Centroid. Let me write it down. So the distance Y is measured from here, up and down. Okay? The reason they put minus here, because if you took the Y, this is, let's look for our simply supported beam. Simply supported beam will be like this. So compression, tension. So if you look to the Y as we go up, Y is positive. So the positive and negative will stay as is. This will give you sigma x to be negative, which is compression. But if you go down, the Y is negative. So negative and negative will give you positive, and this is why this is tension, because the tension is positive. So to take care of the sign, they put this negative sign because the Y distance is going to be here plus and here is negative. And the Y along the neutral axis is 0. Why the bending stress? Why the bending stress is like this? The bending stress, by the way, distribution, you need to know that. Also, sometimes they ask you to, so if you have the rectangular shape, let me use a straight edge here at least to avoid crooked lines. If this is a rectangular shape, so you will find that the bending stress is linear and the maximum at both ends. Okay. This came from sigma is equal minus my over I, where the Y is measured from the neutral axis. Y is positive here and Y is negative here. This is, if this is B and this is H. Okay, and the moment of inertia is BH cubed over 12, as you know. The moment of inertia, the I is equal, in this case, is BH cubed over 12, not over 3, because we take it along the centroid. The distance from here to here, by the way, we call it C. C, and this is C top and C bottom, and they are equal in this case. Okay, so this is also C. So these two C's here. This is why we'll send MC over I. This will give you the maximum here, because the distance Y is increasing from here all the way to the outer fibers, where Y in this case is equal C. This is sigma is equal My over I with the negative sign. If you look to the horizontal shear stress, which is this equation here, tau is equal VQ over IB, you will find that the shear stress is equal 0 at both ends, but along the neutral axis, you will find that the maximum. And the distribution is not linear, it is parabolic distribution, by the way. It's like that. parabola. This came from tau is equal VQ over IB. And tau max is here, by the way, tau max. So the maximum shear stress, or horizontal is called horizontal or transverse, by the way, we call it transverse shear stress, transverse shear stress. Okay, which is given, as I told you, the NCAAS, inherited transverse shear stress, tau is equal VQ over IB. The most difficult part of this is Q. A Q, it does have a name. It's called the first moment of area. First moment of area. First moment of area. A Q is equal A prime Y prime bar. And I'm going to show you. A prime is given and Y prime bar is given. And B is the width. Okay. And the transverse shear flow is equal a Q, lowercase q, okay, is equal VQ over I. Okay, it does not have the B. And this is the equation that we use, by the way, when we are putting the nails. And I'm sure in CE 121, you should know that. We cover this. So I have two pieces. I would like to, this is what we do also in seismic design for diaphragms. I need to nail the upper portion, which we'll call it the, we get different color here. This is the plywood or the sheathing, or in this case we call it, in our case here we call it, this is the flange, and we'll call this is a web. I need to nail this, so I put a nail here. So the nails are spaced at a certain distance, we call it S. How many nails, okay, are needed? We are using this equation to determine the transverse shear flow, okay? The spacing between nails, okay? And you will learn this. So the Q is called the first moment of area, because the moment of inertia I, by the way, I, some textbook, I is equal BH cubed divided by 12, and they are using S, by the way. S is a section modulus. Sorry, I'm not using the S. This is the spacing. Yes. The S is equal I over C, which is called the elastic section modulus, S. So this is also sigma is equal negative M over S, where S is the elastic section, which is I over C. Okay, the distance from the neutral axis, this is the C. Okay, we have C top and C bottom. Okay, this is the distance C from here to here, and this is the distance C also from here to here. All these things are variable, and all these things you will learn it, and I have a lot of problems, and we are going to learn all these things. The first moment of area is the first, this is the most difficult one. And we are going to see this equation, but this is a rectangular section. This is very easy. You will find that the tau max here, the tau max is equal to, you will find is equal 3 over 2 V over A, where V is the shear, and or the maximum shear in this case, and the area is, this A is the area, which in this case is B times H. This equation, we are going to see it, it is only for rectangular and square. Obviously, square is a special case of rectangle square. Okay, and we're going to see from where it came. I believe I did it here for you guys. Nobody will ask you to derive equations, but sometimes I include this just in order to not to waste your time, but in order to make sure that you really understand the subject, because so all these things here, it is M over S. All these equations, I follow exactly the NCAAS. I is equal BH cubed divided by 12, which is the I over C, okay, which is S is equal I over C. Here it is. This one here is a little bit a combination of mechanics of materials and a cantilever beam fixed from one end, 2 kibs per linear foot, and he gave you a T-beam. This is a little bit difficult because it is time consuming, because and he is asking what is the maximum bending stress. Okay, he can say maximum normal stress in bending, or maximum flexure stress, or maximum, okay, normal stress in bending. Okay. The T-beam, it has an issue. The issue is, where is the center? Where is the centroid? This is the centroid for a symmetrical shape like this is piece of cake. But which is the center for a square or for a rectangle, okay, it's piece of cake. But for a T-beam like this, we have to locate the centroid, and we need to go back again to statics, and already we know that. Do you remember the equation? And it will take us back to the parallel axis theorem again one more time. So this is the T-beam. Okay, so this is still called the flange, and this is the web. So he gave us, this is 6 inches, and this is the 2 inches, and this is 4 inches here, and the thickness here is also 2 inches. Is this correct? Yeah, my eyes sometimes Here I know the centroid in the middle. So if this C top and C top bottom are equal, so here C top and C bottom are equal. For a T-beam, no, because the centroid is somewhere here, where the neutral axis, always the neutral axis go through the centroid. Centroid for an area. This is called NA, neutral axis. Here I have 2 C's, and this is why you have to be careful, because what he's asking for the maximum tension or maximum compression or compressive. So I have 2 C's. This we call it C top, and this is we call it C bottom. And they are different, by the way. And since this is a cantilever beam, we know the bending moment for a cantilever beam. It doesn't matter if it is distributed load or concentrated load. In this case, distributed load, I have 2 kPa per linear foot. Two kPa per linear foot. So I need to get this. He's asking for the maximum. So I'm MC over I. But you will say, wait a second, which C I'm going to use? C top or C bottom? After we determine the location of the neutral axis, we are going to get where is the C top and the C bottom, or how much is the magnitude of each. It depends on the question. He's asking what is the maximum bending stress. He didn't tell me maximum tension or maximum compression. Vague. Okay, so in this case, I know the beam will deflect like this. This is happy phase or unhappy phase, unhappy phase, because this tension and this compression. The upper fibers will be tension and the lower fibers will be in compression. So in this case, it's going to be a negative bending moment. This is similar to the problem I solved before. So he said the maximum. So in this case, since he's saying the maximum, I will take the larger of the two. Because the I is the I, is moment of inertia. This is constant for this given area. Moment, I'm going to use the maximum moment, Mmax. So in this case, I can write this sigma max is equal to Mmax times C max divided by I. I is I. It's only one I. Any given area exists on Earth, it does have only one I. Okay? So far, so good? So we need to look at this. How far from here to here, which you normally will call it Y bar or Y bar. Okay? And the Y bar is given by this equation. Here it is. Or Y neutral axis. Or Y at the centroid. The centroid for an area. So basically, you are going to divide this into 2 areas as we learn in the statics. And you have to locate where is the datum, because this is my reference line here. So I said that it is 4 times 2 times 2 because I know the centroid is 2, and 2 times 6 times 5, 5 because it's 4 and 1 is 5, divided by, so 3.8 inches. That means that this here, this y bar here, or y is equal to 3.8 inches. Since I know the whole distance is 6, that means that the C top is equal what? This is the C bottom, is 6 minus 3.8, so this will give you 2.2. So in my calculation, since he's asking for the maximum, I have to use a 3.8 inches because I'm asking for the maximum flexural stress or the maximum bending stress. Okay, so, oh my God, time is flying and I'm behind. So let us do our best here. So after getting the centroid, we have another problem. This here, the moment of inertia was BH cubed divided by 12 because it is a symmetrical shape. But for a T-beam, you have to use the parallel axis theorem. The one we talked about it before. You remember in statics? I did it one more time here for you, and I will leave this to you because you already are expert now. So now the moment of inertia about the centroid using the parallel axis theorem. Here it is. And here I need you to understand that. I know it's not an easy, but this is a general equation. And here we are applying the parallel axis theorem. Can he give you something like this on the exam? I really don't know. Okay. But if you are given a problem like this on the exam, don't forget that you have 3 minutes per question. Only 3 minutes. Okay, so I don't like to spin. I don't like you to insist on a problem that you know how to do it, but it will take more than 3 minutes. I need you, because all questions are equal weight. And in order to pass this exam, you must, 3 things normally I mention. As a suggestion, is up to you. You can do whatever you would like to do. You are the boss. Okay, you can do whatever you want to do. But this is just a suggestion from Dr. Mansour based on my personal experience over all these years. Okay, so number 1, you need to understand the concept very well. If you don't understand the concept, any change or variation or deviation from any given problem, don't say that, okay, I know how to solve it. But if they change a little, this is why the concept is very, very important. Number 2, what is this number here? Million, okay, not billion, million, okay? I will use only million today. Million times a practice. I don't have any practice and the practice and the practice. I mean, I will repeat this million times, but here it is, a practice. A practice by solving problems. Solving problems. Okay? I believe that I provided you in this chapter so far enough problems. I believe if you understand them, I believe you're going to be in very good shape. And I don't know how many of you finished all the problems last time. I mentioned if we add all the problems, I believe we ended with a reasonable number. I don't know. I can remember what's the number, but I forgot. I mentioned it somewhere here. It is 28 problems, I believe. And so I wrote it somewhere here. So I need you to practice and the practice and the practice. I remember I wrote them somewhere here. So we need to make sure that we are really having enough practice, okay, problems, because practicing and the practicing and the practicing. Okay, and if you are not satisfied with the problem that I'm providing, and you have access, there are many books available in the market. You are very welcome to purchase any book or whatever book you believe that you feel comfort with. Okay, solve problems. And the step number 3 or what I recommend is you need to go to the exam well prepared, number 1, and you need to go to the exam with a strategy. And this is what I'm talking about, the strategy. If you read this problem and you know Yes, you can do it, but will take more than 3 minutes. And I'm sure that it will take more than 3 minutes. Probably I will flag it. As you know, this is a CBT exam, computer-based test, and you can flag the questions. Flag it, okay? You can just put a tick mark next to it or whatever system they are using. Persons, okay, flag it. You need to come back again to answer all the questions that you flagged. But I flag it, I need to skip it to go to another easy question. Probably it will take only 1 minute because I need to gather points. I need to collect. I don't like to go home and say, oh my God, I solved the most difficult problem on the exam. But it took more than 3 minutes and you are going to be, okay, losing time. So this is a moment of inertia. After that, I calculated the bending moment, exactly the same we did before. Please look to that. This is the easy one. And after that, we apply. And as you can see, what C did I use? Excuse me. I used the larger C. This is the C max. Or the larger C. There are two. Larger C. Why? Because he said, what is the maximum? He can change this. He said that the minimum. If we change one word, the answer will be different. In this case, what I'm going to use? I'm going to use the smaller C. You see, one word can change the answer that I should select based on the. So please do all these things. Let's move on. Here it is another. This is an easy one. Okay, cantilever beam. It does have a concentrated load. The maximum bending of flexure stress in the beam, BH cubed. This is an easy one because this is the second moment of area. And sigma is equal MC over I. C is the same. C top and C bottom because this is a symmetrical section. And here it is. I try to write as much as I can. Let's take a few minutes of break. Right now is about 5:55. I need to just get some fresh air. Okay. Fresh air without corona, please. Okay. So we need to make sure that we are taking all the necessary precautions to stay healthy and stay safe. So let's take a few minutes. So 10 minutes from now. So it is 5 right now 55. So 6:05, please. Thank you. Okay, welcome back everybody after this short break. Let's the second section here I discussed briefly also the transverse shear stress, which is tau. Obviously, sometimes I'm providing a little bit of theory, a little bit, not in depth, but basically tau is equal VQ over IB. This is the first equation. And this is, by the way, the shear flow, which is Q is equal VQ over I, which is given in the NCEES. Let me move to the second page here. Here it is. So this is on page 136. I will try to do my best to show you exactly where these equations. So basically, sigma, and I showed you all these things. So this is a section that we talked about it before, and this is the shear flow, the transverse shear flow, or just simply the shear flow, which is equal lowercase q is equal VQ over I, which is this one here, the shear flow. Okay, this is again explanation. This table here is giving you like a little bit sign convention, obviously. Shear, we have something called direct shear and indirect shear. The indirect shear, this one here already we saw it, which is due to torsion. Let me see, I don't have the, so due to torsion, so this is the one we talked about it. Okay, so this is applied torque T, and if you look to the, and you remember the piece of chalk that I twisted, and I showed you the, so, and this is R, the radius, and the J is equal the polar moment of inertia, which is Ix plus Iy. This is indirect, but the direct shear, this is when you have members are connected together, either by rivet or by glue or by bolt. Okay, so if you have two plates, you connect them together with some kind of, you drill a hole and you are bolting them together with a bolt. Okay, and you apply a force P. This is a single shear. Why single shear? Because this bolt, okay, this bolt is going to be sheared in one plane, so it is tau is equal P over A. But if we do have two surfaces or two areas that will be sheared, like I have three plates are connected together, okay, so if this is the rivet or the bolt or screw, whatever you'd like to call it, here it is. In this case, this is P over 2, and this is P over 2, and this is P. So right now I have two areas that will be sheared out. So this rivet, okay, or this bolt, okay. We have one area here and one area, which is this here, these two areas. Okay, so this is why we divide by 2, because there are two areas. Or you can look at it from one side, that B over 2, but shear one area, so it is the same. So it's called double shear. Okay, this is, so we call this direct shear stress, or the textbooks they call it direct shear stress. The one in our hands right now, it is, or in front of us is, it is the transverse shear stress due to bending, which, as I told you, call it a transverse shear stress due to bending. Okay, Q is the first moment of area, and this is the integration of, so Q, the uppercase Q, by the way, is equal the first moment of area, moment, and it's given as, let me see here, it is A prime Y prime bar, as given in the NCEES. The first moment of area, here it is. The first moment of area, above or below the point where the shear stress is to be determined. This is Q. This is on page 136 of the NCEES. So this one here, I was telling you that for a rectangular or square cross sections, the maximum transverse shear stress, which is horizontal shear stress, sometimes we call it, is occurring at the neutral axis, like this here it is, which is, I told you that the shear stress here is 0 and 0. This is a rectangular shape, and the maximum along the neutral axis, this is NA. This is the neutral axis. Okay, I don't know if they provide this equation or not, but just for your knowledge, that for a rectangle, so when we say tau is equal VQ over IB. So if you do have a rectangular shape, this is B and this is H. Okay, so V, what's the Q? This is the neutral axis. So a Q is equal A bar Y bar prime. So what is the Q above this neutral axis? This is the area. It's called the first moment of area. So the area is equal B times what is this here is H over 2. So this is the area. And what is the Y bar prime? Okay, the distance from the centroid to the neutral axis, which in this case is H over 4. So you'll find that the first moment of area, or Q, is equal BH squared divided by 8. So if you put this BH cubed, BH squared, sorry, divided by 8, divided by the moment of inertia I is BH cubed divided by 12. And B is B. If we simplify this, you will find that H squared with H cubed, I have H, and B will cancel with B. And 12 in the numerator, 12 over 8 times V divided by B times H. Okay, this is what is left. So this is the 3 over 2, or 1.5, V over A, where A is the area of the cross section of this, which is B times A. This is only for a special case because of the Q that, okay, so this only for a square, as I mentioned, square, rectangular sections only. Okay, and this is what I mentioned. Here it is. I needed to pay attention. This is the chapter I'm providing. Here it is. This is on page 42. Page 42 of the chapter 6. So I need to move fast because I need to wrap up this chapter today. You have a problem, 25. This is a T-beam again, also. Excuse me. Inverted T. Okay, this inverted T-beam. First, we need to locate the centroid, which is, again, is a very good exercise to, I needed to know how to do that. Here it is. I broke it down into 2 pieces, as you know, the neutral axis. And after that, we need to get the moment of inertia using the parallel axis theorem again. Oh my God. I needed to know this. And this is the Q. The Q, it is above or below, by the way. Q, when we calculate Q, is the first moment of area. I calculate the Q here for the rectangular section, the area above the neutral axis. If you calculate the area below the neutral axis, you should get the same. So if you have a T-beam, like the one we have in this sample problem, and the neutral axis is here, after you locate the distance y bar, the Q at this interface between the flange and the web, it is this here, only this area. The neutral, the Q at the neutral axis is equal to the entire area above. And instead of using the two areas here, I can use one area at the bottom. It should give you the same. So the Q, if you calculate it from the area above or area below, will be the same. Okay, I need you to be aware of that. Okay, and why the shear stress? In fact, for this rectangular shape, no, not rectangular, sorry, for this T-beam, the transverse shear stress distribution is like this. And I believe I have a problem if I remember, I included, because they might ask you about this. Excuse me, the allergies is okay. So if you look to this, so the neutral axis somewhere here, where the maximum shear stress will be. But if you look to the distribution of the I estimated the neutral axis to be here. I don't have exact figure, exact location, because I don't know the dimension, but I need. So the equation tau is equal VQ over IB will give us the following distribution. The shear stress is equal 0 here. And it is non-linear, it's parabolic, comes at the interface between the flange and the web, and immediately it will jump. Because at one point of time, I'm using the width of the flange. This is the flange, and this is the web. So what is B will be used? One time I'm dividing by a larger number, which is this one here. This will give me the shear stress here. The moment I transfer from here to here, I have a smaller B, which is the width of the web. So this is why the shear stress is jumping. And after that, it will increase the maximum and start to come down. And here it is. This is a tau max. And always the maximum horizontal shear stress or the maximum transverse shear stress will be at the neutral axis, which is opposite to the bending stress. The bending stress here is equal 0. And the bending stress at the outer fibers will be the maximum, which I need you to know this. Okay. I know you have tons of questions, but forgive me that I have to move on and try to solve as many problems as we can, and we'll finish as much as we can, and I will be glad to go over. Okay. All these things are combined stresses, which is combined stresses. I included one section in about combined stresses. So the combined stresses, I don't know if they can. Tau max is the maximum shear stress. Yeah. Tau max is the maximum shear stress. Tau max is the maximum shear stress. That's correct. This is the maximum shear stress that will occur along or at the neutral axis, which is this tau max. That's correct. Maximum shear stress. The shear stress here is 0, and the shear stress is equal 0. And at any point, we can calculate the shear stress if I know the numerical values. And you have some problems, by the way. But the tau max is the maximum a transverse shear stress. Okay. I included one section here. Let me see if I am combined stresses. Okay, now combined stresses. Probably I put it. It is coming in another section. if I do have bending and axial tension and bending and axial compression, or bending and torsion. When you have, for example, bending and axial tension, let's assume that you have a cantilever beam. And we'll cover this in timber design. Okay. Some of you took the class already, the timber design by Dr. Breyer's book. Okay, this book here, Design of Wood Structure, this is the 7th, and the 8th edition is the one I used it last semester. We cover, for wood design, there are some members, they have combined, okay, bending, and here it is. For example, okay, combined bending and combined compression. All these things you will learn it, okay, because it's very, very important, okay, very, very important to know, because the beams could not necessarily be subjected to only one type of bending stress or one type of stress, but it could be both. So the combined stresses are very, very important in design. So, and you will learn this for sure, or you already learned it in the KF. So if you have a cantilever beam that's subjected to axial load like this, P, but also subjected to a force like this, F, tension. So I have this force will cause tension, and this force will cause bending. So sigma is equal plus or minus MC over I, and B over A. B over A, let me make this P, okay, and this is F. Okay, this called combined, okay, bending and tension. Bending and compression, the same cantilever beam could be subjected to the same F, but it will be a compression force P. And you can see here is minus, because tension, we said that this is positive, so this is tension, and this is compression. Okay, so combined stresses, and the last combined type of stress I need you to be aware of is torsion and bending. You have a shaft, okay, or remember, subjected to torque, but also subjected to what? To a force, F. So this torque will cause TR divided by J, and MC over R is due to this. So I have bending and torsion. And I believe I have some problems. I know it's a very lengthy one. Okay, this problems 26. Even I draw it more circle. So you have an L shape like this, or some kind of mechanism as shown fixed here, and you have a force here. So this force P is going to create torsion. If you come here, torsion, and is going to create, because I can come here, add 1P here and subtract 1P. So I did nothing as far as equilibrium. Okay. This P and this P, two forces equal magnitude, opposite direction, is going to create what? Torque, which is the torsion in this case. So the torsion is equal P times A. And here it is. M is equal P times, oops, no. Where is the torque? Here it is in the front of me, but I missed it. Sorry. Okay. Torque T is equal P times A. Okay. And the bending moment in this case, so the bending moment, so this is the torque. Okay. And the bending moment is equal this force P times whatever distance he's asking about, distance, the point D. So this is the force. So these are gone. So B times the distance B, which is the bending moment. So it's a very interesting problem. Look at it. So I have two. I have torque and I have bending moment. And in this case, sigma is equal my over I, and tau is equal TR divided by J. And we are going to use the combined stresses. And I use more circle again to illustrate that, which is the same concept as I told you before. Deflection. Deflection, all bodies are subject to deflection, or all bodies are deformable bodies. So the NCEES provided this section here in front of us for the deflection. Obviously, integration and constant of integration, all these things, I don't expect that we are going to do that. So 1 over rho is equal M over EI. Okay, and with the differential equation, and we can get the constant of integration, and we can solve for the deflection, which they are using Y, by the way. Y is for deflection. Okay. This is, again, it is the integration method using the 1 over rho. The rho is a curvature, by the way. This differential equation of the deflection shape. So this is, if you have a beam, and this is rho. So in this case, 1 over rho is equal M over EI, and we can integrate, and we do that. And probably I provided all these things, and we did this, by the way, or you did it in mechanics of material. But here, for the sake of NCEES, I don't expect that he will ask you to do any calculations. But they provide us with series of tables. Already I talked about the tables here, by the way. The NCEES on page 138. I talked about this table before. Do you remember this table? Okay. And I talked about this table also on page 139. And after that, he gave us these tables here that it does have the different beams with different loading conditions. And we need to understand these cases and what are these numbers, or this equation, sorry, first, before numbers. So if you go to page 140 of the NCEES, if you don't have the book with you, also I included in the chapter that I gave it to you guys. So I have it here somewhere. Composite columns. Here they are. So I'm providing also the same two tables that we talked about them before, which is table 1 and table 2, which is material properties. So table 1 and table 2. And here are the tables that it does have: simply supported beam, slopes, and deflection, which is this one here. And from the NCEES, this landscape. Okay. So you don't need to go and calculate or derive the equations for deflections, because already they did it for us. So there is no need to reinvent the wheel again, as we say. But we need to be careful how can we use these equations and what are the parameters. So this is a simply supported beam. Okay, there is a load in the middle, L over 2 and L over 2. And this is X, and this is, they use V. As I told you, use V. This is on page 140, please, of the NCEES. So the first column here is called the slope, and they are using angle theta. What is the slope? The slope is the angle between the deflected shape of the beam and the original shape of the beam. The beam was originally horizontal. Okay, but the beam is deflected as shown. This is the deflected shape of the beam. This is the angle theta, which you draw a tangent and measure it from horizontal. So this is called the slope. Slope. The slope is not dy by dx in this case. No, this is a tangent to the elastic curve, and we can derive that. The second column is deflection. V max. The maximum deflection will be, here it is, at the center, under the load, is equal negative PL cubed over 48 EI. Okay, the negative indicating is coming down because this is V, this is positive, and since it's coming down, this way they put negative here. Can you see the diagrams? I know this is the so this is the second column, which is the deflection. Okay, the following column is the elastic curve. This is the equation that is representing this shape. Okay, the deflection V, this is V max. But I can get the deflection at any point using the equation of the elastic curve, which is given by this equation, and put the limits, but be careful with the limits. Obviously, when the x is starting from here, by the way, this is the origin here. This is the origin here, 0 and 0 here. So the x start, this is, so my origin is here, and this is the V. They use it V for deflection instead of Y, and x started from here. The second one is a maximum M max, which is BL over 4. So all these equations for this unique case, you cannot use it for any other cases, okay, or for any other loading condition. So they give us another case where I have a concentrated load P, but at a distance A and at a distance B, and this is still L. By the way, this span is L, this is in the middle, this mid span. Again, they derived equations for us. And we need to be aware of that. Okay? Here, he is giving you a simply supported beam, but it does have a concentrated moment, M. Okay? This is a simply supported beam carrying a uniform load W. And you remember 5 WL to the 4 divided by 384 EI. And this is the theta. And this is the elastic curve. And this is the bending moment, which is WL squared divided by 8. Do you remember WL squared divided by 8? Here it is, which is the maximum bending moment in a simply supported beam carrying a uniform load. Okay? So if you do have a simply supported beam, you come to this case. If you have a bending moment acting at one end as shown, and so on, you need to pick the case that it match, okay, matches the given problem. Okay, this is a load, distributed load, okay, but it is half at L over 2, and L over 2 is not the entire beam. This is a triangular load starting from 0 to the maximum here, and the same story. Okay, so we need to be aware of this is a cantilever beam. For cantilever beams, okay, they are giving us a concentrated load at any point, distributed load, bending moment, triangular load, and so on. So all these cases, by the way, they are giving again slope, deflection, elastic curve, and the maximum bending moment. And they ended with the general case. Okay, if you have it, basically it must match exactly. So we pick all these given are these equations are given in the textbooks, but nobody will ask you to derive. We can derive all these equations. So deflection is very, very important, and we need to be aware of the deflection calculations. And so if you go to the NCAAS, which already I copied these equations, and I have it here. Here we go. I'm going back to the chapter that I'm providing on page 47. You will find all these equations. I talked about it. I explained it also as simple as I can. And I have some problem 27. By the way, deflection delta, or V in this case, he is using V, which is a deflection. For example, this one here, which is PL cubed over 3 EI. This is a deflection due to what? This is due to concentrated load at the free end. If you have a cantilever beam, and this is P, so this is going to be the Vmax. I use delta, probably I will use the Vmax to match maximum deflection. But this is due to concentrated load. But he gave me a distributed load, W. W is given to be 1 kip per linear foot. So I put this equation intentionally, say, wait a second, are you going to figure this out? Okay, yes, you should. Because if you look to the equation they provided for the cantilever beam, which is this one here, and the reason I put it over there, this is a cantilever beam, but the P is not at the free end. But he gave you the equation for deflection. Let me show it to you. It is, let me put it in my notes, at least you can receive the notes. So you can, because on the exam, I noticed that they give you something, it doesn't match exactly the cases they are giving you, and they are expecting that you will be or you understand the concept to a degree that you can figure it out. They will give you this scenario. A cantilever beam, it has P is equal 6 kips. And the L is equal 8 feet. And it will give you the cross section is 4 inches by 6 inches. And let's assume E is equal to be, okay, 30 million PSI. PSI. This is what is given. Consider this is a problem. I just made it, a cantilever beam. It has, so let me give you 3 minutes. Okay? What is the Vmax, maximum deflection? And we are going to get answer A and B and C and D. I need you to participate. Okay, you have calculators, and I give you everything. E is given, the cross section is given, P is given, L is given. Let me give you 3 minutes from now. Now it is 6:39 California time, 6:40. So 6:43, I will collect the answers from you guys to see what. And I need it to be in inches, by the way. Sorry, I should mention that, inches. I need deflection normally inches or millimeter, not in feet. Because it's a small quantity normally. So units are very, very important. Okay. Okay. So if you look to the NCEES, I don't know how many of you finished it. Anybody? Did anybody come up with an answer? Just to, you can write it down. Okay, whatever answer you came up with. Okay, not answer yet. Okay, or no answers. Okay. First of all, you need this is given the given cantilever beam, and this is a cross section. Okay. Oh, here we have an engineer. He came up with a number, which is good news. Okay. So it is 0.21. I got an answer 0.21 inches. Okay, let us take one answer from our friend. 0.21 inches. This is giving you a test that probably some problems they will take longer than the 3 minutes. I give you in fact 4 minutes. But first of all, you need to match the case that's given case with one of those cases given in the NCEES. You will not find one. But they give us the general case, which is the equation here. I just put it here. This is if the load is acting somewhere here at a distance here, call it A. But if the load is moved all the way to the end of this beam, so A is equal what? L. So if I put A is equal L negative P L square divided by 6 EI times a 3L minus L. This is A is equal N in this case. So this will give you a negative B L square. I have here 2L and 6 EI. This will give you negative B L cubed divided by 3 EI. So this is the equation you're supposed to use. And this is why I put it in my book. For a reason, I need you to be aware of that. I need you to be aware of this, that they might give you a case, not necessarily to match what is given, so we need to be ready. So this is the V is equal PL cubed over 3 EI. This is for the cantilever beam carrying a concentrated load at the free end. So this is the values that I put this here. Okay, but this is a distributed load. Do we have a case like this? Yes, we do have case. Okay, so but let us solve. This is the case. This is the case here, which is deflection is equal WL to the 4 divided by 8 EI with the negative sign, as I told you, because this is positive and this is negative. So it's just coming down. It's just a matter of sign convention. Excuse me. Units are very, very important in deflection calculations. And the mistakes that could happen, this in PSI, this is in feet, this is in kips, and this is in inches. Mix. Oranges and banana and apples. We need to have all of them to be the same unit. So first of all, I need to decide which equation should be used. So this is the general equation, and we do have where the load is acting at the free end or at the end of the beam. So A is equal L in this case. So we came up with the PL cubed divided by 3 EI. So right now, so the Vmax is equal negative PL cubed divided by 3 EI. So negative. What is P? P is equal 6 kips. So 6 kip. A kip is equal 1,000 pound per kip. L. What is L? L is 8 feet, but I need it to be in inches. So 8 times feet times 12 inches per foot. This is cubed. Divided by 3. I gave you the modulus of elasticity E to be 30 million PSI. So 30 times 10 to the 6 pound per inch square. And the moment of inertia I for a rectangular section is equal BH cubed divided by 12. This is 4 inches, 6 cubed divided by 12. So you'll find that a kip will cancel with kip. Pound will cancel with pound. This is feet will cancel with feet. So this is inch cubed. And I have here inch square. And I have here inch to the 4th. So you'll find the numerator is inch to the 5th power. And the denominator is inch to the 4th. So this will cancel with this. And the end result is going to be inches. And this is easy for the concentrated load. For distributed load is a little bit tricky also. So if you do this piece of calculation, did I miss anything? Did anybody notice that I missed anything? So it'd be L cubed divided by 3. I believe I missed the 3. Okay, 3 EI. Okay, so let us do it in 22 seconds to see if you are going to come up or are going to come up with the same. Let me see, I have a calculator here. I think here it is. Any calculator you are using or calculators, you need to practice enough in order to make sure that, excuse me. So let me do it, and if I'm going to come up with the same answer that one of you already provided. I got a number, 0.8192 inches. Let me do it one more time, unless I missed something here. So it is 6. One more time, please. 3 times. Normally, I do the calculation twice, because I might be wrong the first time. Maybe our friend was correct. And I got the same number. I got the same number, 0.8192. Do you agree? Anybody agree with me? Okay, support me, please. Okay, please. Okay, I need support. Okay, I need you to participate. Okay, I just made the problem, so I don't know what is the answer. But the point is, okay. Oh, that's good. So you support me, my friend. Thank you very much for your help and your support. So the point I would like to make here is units. And this is easy for the distributed, for concentrated load. The distributed load problem I gave you even more difficult as far as units. It's so tricky. And I'm talking about this problem here. So, and this what I need you to do. I will stop in 5 minutes because the allergy again is bothering me after it seemed that when I went out to get some fresh air, the fresh air came with the allergy and it's bothering me too much. So we are going to meet on Saturday and on Sunday, so we'll go over, and I'm keep also working on the other chapters. Hopefully I can squeeze all these chapters, transportation and geotechnical and construction and surveying, all these things. I will do all my best to help you guys as much as I can. So what I need from you, the 627, the maximum deflection, you have, this is a cantilever beam, W is given, E is given, I is given, L is given. And I put here none of the above. On the exam, they don't have none of the above, but I put it here in order to make sure that you are really going to work hard and see, and be careful with units. The deflection here, this maximum deflection will be at the free end, by the way. The beam will deflect as shown, like that. And this is the maximum V, or V max. And this is given by this equation, which is negative, okay, WL to the 4 divided by 8EI. This is to the 4th power. This is negative WL to the 4th divided by 8EI. 8EI. Is this correct? Did I copy it correctly? Oh, yes. Okay, so this is the maximum deflection. Okay. And not necessarily he is going to ask you for the maximum deflection. He will tell you what is the deflection at 2 feet from this here. So he'll give you 2 feet. If the L is given to be 20 feet, he will ask what is the deflection at 2 feet from here. So what I'm going to use, I'm going to use this equation. This is fixed here, and this is the free end, and this is X. X is equal 0 here, because the deflection here is 0. Because if you look to this equation, if you put X is equal 0, this will be gone. Here it is, WX square, X is 0, so there's no deflection at the fixed end. So I need you to be aware of that. So please do this, and I need you to go over all these problems. As I told you at the end of this chapter, here it is. You will find the problem 6.1 all the way until 6, and it has a lot of calculations, by the way, until 6. Okay, for example, here it is, cantilever beam and shear moment diagram and all these things that until problem 6.28. So you have a bunch of problems, and I need you to be aware of that. I need to be capable of solving all this, and I solve it for you already, but I need you to be aware of the process and units, and the most important thing is to what is the appropriate equation, or what is the or what equation should be selected or should be used. Okay, forgive me, I have to stop here, and I will join you again. And thank you very much for adjusting your schedule to match my schedule, the business schedule. But never give up. You just keep studying and keep doing all your best. Come up with questions. I enjoy questions, and if there is anything I can help you with, for sure I will do this. Just pray for me to stay healthy, and I'll pray for you to stay healthy. As long as we are healthy, we are wealthy. Okay, so as you know that do you remember from high school this statement? Probably I mentioned this before. What's his name? Patrick Henry. Patrick Henry. He mentions that. He said that what Patrick Henry said. Do you remember from high school? For those who graduated from here, they should remember Patrick Henry. excuse me. Patrick Henry said, give me liberty or give me death. Give me liberty or give me death. Do you remember this statement? Search it tonight. I know Google nowadays. Dr. Google is available for you guys. Not in our days. So give me liberty or give me death. This is Patrick Henry, to the best of my knowledge. Correct me if I'm wrong. Patrick Henry. Okay, Henry. Okay. So I joke with the engineers. I used to work with them. So I just switch or not modified, not switch, modified. When I'm not feeling well, I'm not. So I modified Patrick Henry's statement. He said, give me liberty. Okay, I said, give me health or give me death. Okay. Okay, give me health or give me death. Okay. Because I don't like to be sick. Okay, that's because sickness is not good. So let's stay healthy, because and when the moment comes, okay, of the death, we need it to be. I need it to be sudden like that. Just very quick. Okay, give me health or give me death. Okay, so my engineers, or the one I used to work with them, or my fellow engineers, they used to laugh and say, "Oh, Dr. Mansour, this is a good statement." I don't know. It's just I hope that Patrick Henry is not upset with me. Okay, stay healthy, please. Okay, so and let us do our best, and I will keep communicating with you guys, and I will do all my best to help. I'm extremely busy, and as I told you that sometimes I forget did I eat or not, but one day I will slow down. But I wish you the best. Okay, good night, everybody. Bye bye. Okay, Michael, yes, you mentioned that. Yes, sure. Okay. I will take care of that. I will take care of that. Yes. All of you, I will take care of you. I know there is a lot of emails, and you missed the first. I'm working with the webmaster, as I told you, that all the handwritten notes, I will scan it and send it to you, unless I did some. And the webmaster, he's supposed to come tomorrow. I loaded all of them on the Google Drive. I convert them to the proper format, and I load them on the Google Drive. But I was telling him, instead of emailing you the link to the Google Drive, if there is a much easier way for me, because I'm really busy, and I will take care of that. I know some of you missed, and some of you sent emails, and no, I'm not ignoring anybody, believe me. It's just a matter of the time, and we will do it. Good night, everybody.